I'm Andrea Wilson, Director of the Center for Population, Aging and Health, and I'm pleased to introduce our final Stats and Data Series speaker today. Before I do so, though, Zenny has passed around some slips of paper, and if you have any suggestions for topics or speakers that you'd be interested in hearing next year, please jot those down, and you can just return them to Zenny at the end of the talk. We'd really appreciate that. So today, I'm happy to introduce a graduate from the Western's Economics Department, Ivan Medovikov.
That's right.
And he's now an assistant professor at Brock. This talk today is a follow-up to a talk that he gave last year on time series models, and today is going to talk about applications of those. So welcome, and thank you.
Well, thanks very much. Thanks for the introduction. So hello, everyone. Thank you for coming, and welcome to the Applied Series Topics talk. So this talk really is intended as a sequel to the Introduction to Time Series talk, which I gave as part of the RDC series last year. So for that reason, I tried to keep kind of the intersection between the two talks fairly small. So there's a lot of subjects which are very kind of important in time series analysis that are not going to be covered in this talk, but which were covered in the Intro to Time Series talk last year. So if you're new to time series, I believe the slides from the last year's talk are actually available on the RDC website, so you can look at those. So similarly to the last year's talk, this talk is intended to be at a fairly introductory level. So I will purposefully be omitting a lot of details. But if you'd like to get basically some additional information about any of the concepts that I'm going to talk about today, so please feel free to let me know. I'll be happy to provide you with some references where you can get kind of more info on this. So the idea for today's talk is to focus on some of the issues which are highly relevant to virtually anyone doing kind of applied time series analysis. So in particular, I want to begin today's talk by talking about the issue of stationarity versus non-stationarity. This is something that I actually did talk about during the last year's talk, so during the Intro to Time Series talk, but I want to go over that real quick again because the issue of stationarity really is quite central to the time series analysis. And just in case you've missed the last year's talk, I wouldn't want you to miss that. For the bulk of today's talk, I thought I'd focus on issues surrounding trends and seasonal cycles in the data. So you may have came across time series which have been kind of detrended or seasonally adjusted. I think Statistics Canada, most of the macroeconomic series are adjusted in some way, so they may be adjusted for business cycles and such. But it's not always clear, I find, as to exactly what this process of seasonal adjustment actually entails. So today I wanted to spend a fair amount of time just talking about the problem of modeling seasonal cycles, as well as the problem of seasonally adjusting the data. Because in practice, when you work with time series, that's an issue that tends to come up. And if we have time, and I think we certainly should have time, I would also like to talk a little bit about the problems of time series forecasting, and in particular about the problem of model evaluation. So suppose that you had two models which are reasonably similar in terms of their complexity, and suppose that you'd like to use these models to actually forecast something. Basically, the problem then is how would you decide which model does a better job at forecasting? And there is a number of approaches to that problem. So if you recall from the Introduction to Time Series talk, the issue of stationarity was really quite central to the analysis of time series. So we say that a time series is stationary when the mean and the variance of the time series does not change over time. So if basically the nature of the series doesn't really change across time. And believe it or not, but actually it's not that easy to find examples of series. At least I find that it's not very easy to come up with examples of processes which are stationary, especially in the longer term. Because in nature, especially over longer periods of time, things tend to kind of change and evolve in one way or another. So one example of stationary time series could be radio static. So for example, if you tune your radio to an empty frequency, you're going to hear the static, which is going to have some pitch and tone, and that pitch and tone is pretty much going to be constant over time. So if you had a radio 1,000 years ago, and if you tuned it on to an empty frequency, presumably all frequencies were empty 1,000 years ago, so you'd hear static, which would have exactly the same pitch and tone as it has today. So that's like something that really kind of stayed fairly constant over time. But most things in nature do not stay constant over time. So they drift, they do have some kind of a trend. So for example, human population, and in this case, if time series has some kind of a trend, so if the mean or the variance of the time series tends to kind of be non-constant and tends to move in a certain direction or just change in some way, we say that the time series is non-stationary. So it's much easier to come up with examples of non-stationary time series. So things like population, for example, is highly non-stationary. In fact, it's growing at an ever-increasing rate. Things like GDP is certainly non-stationary. It has a very clear upward trend. So it has been growing at a fairly steady rate over the past, let's say, 15 or 20 years. So things like weather, for example, temperature at a certain point on Earth is again an example of highly non-stationary time series. It tends to follow a certain cycle, so the average temperature in winter is certainly not the same as the average daily temperature in summer. So kind of almost, I don't want to say most of the things, but many of the time series which you may come across are going to be non-stationary by their nature. So here I have two examples, two plots of two time series. So one of them is stationary, and that's example in the first plot. So you can see that basically whenever you have a stationary time series, it's going to be wiggling around some constant mean across time with roughly the same variance. It's not going to be kind of diverging in any direction. If you have a non-stationary time series, this time series will diverge away from the mean. So on the second panel over here, you can see that the series kind of starts around some mean, but then really diverges away from that mean and never really comes back. So graphically, that's how would the difference between the stationary and non-stationary time series actually look like. So you may wonder, well, why is it that you need to worry about that issue of stationarity? So what's so special about stationary versus non-stationary data? Well, it turns out that if your data are stationary, you really don't need to worry all that much. So it turns out that when you're working with stationary data, assuming that you have no other issues with your model or with your data, the usual econometric techniques and the usual statistical techniques will work pretty much in exactly the same way as they would work if you had a kind of cross-sectional data. So your OLS estimates, for example, will, again, assuming that you have no other problems with your model or with your data, will be unbiased efficient, so you'd be able to do the usual t-tests, f-tests, using these time series data, again, if they're stationary and if you have no other problems with these data or with your model. But if the time series, in fact, is non-stationary, in this case, things can break down quite badly and also quite quickly. So in general, if you're fitting a model using non-stationary data, and if you fail to correctly take this non-stationarity into the account, you'll generally get essentially spurious regression results. So your estimates are going to be biased. Your t-tests will not really have much meaning. So the regression results which you would get are essentially going to have no meaning. There's just going to be some random numbers that you shouldn't be paying much attention to. And in practice, the situation which you may find yourself in when you use when you fit a regression model using non-stationary data, you may find that your p-values are going to be extremely low. Your R-squared is going to be extremely high, let's say 99.999%. So the model is going to look the model fit is going to look a little bit too good to be true. And that's because it's not true. Basically, that could be a signal that your data, in fact, are non-stationary. So it's very important to keep that in mind and to make sure that when you're working with time series, you are either working with stationary series or you're taking the non-stationarity into the account when you're doing your estimations. And there is a number of ways, a number of methods, a number of tools which are available for the testing for non-stationarity. So both formal kind of methods. Among the formal tests for non-stationarity, perhaps the most widely used one is the augmented Dickey-Fuller unit root test. And that's something that I talked about in the Introduction to Time Series talk. So I'm not going to talk about that today. Informally, perhaps one of the most kind of commonly used tools for the detection of non-stationarity is the so-called autocorrelation function, or ACF, and that's again was something that I covered in the last year's talk, so I'm not going to focus on that today. There is another tool which is really quite useful, which is also often used to detect non-stationarity, and I haven't mentioned that during the last year's talk, so I'm going to talk about that today quite a fair bit, and that's the so-called normal quantile plot, or the QQ plot. So it turns out that when you're fitting a regression model using time series data, and it turns out that if your data are stationary, if your model is correctly specified, so if you don't have any problems with your regression, under the usual assumptions, under the usual regression assumptions, the residuals from your regression should be normally distributed. But if you're feeding non-stationary data into the model, this may manifest itself, and this may actually show up in the residuals, and as a consequence, you may get residuals which are not normally distributed. So then kind of one approach which is sometimes used to one method of diagnostic for non-stationarity, which is sometimes used, is to look at the residuals from your regression model and see if these residuals appear to be normally distributed. So if your residuals roughly follow the normal bell curve in this case, you would say that yes, it seems that the model doesn't have any problems, the residuals are what they should be like. But if you see that your residuals are not normally distributed, that could be basically interpreted as evidence that you do have problems somewhere. So for example, you may be working either with non-stationary data or your model may be basically incorrectly specified. So then the idea behind the QQ plot is to look at the quantiles of your residuals and compare them to the quantiles from the normal distribution. So if the quantiles match, you would say that, well, the residuals do appear to be normally distributed, and therefore kind of I'm happy with the model. But then if they do not match, this could be interpreted as evidence that you do have problems somewhere. So here I have two examples of QQ plots. So the example on the left shows a QQ plot for a sample which was drawn from a normal distribution. Now the blue markers, so the blue points, these are the quantiles which were obtained from the sample. The red markers, so the red markers over here, these are the quantiles from the normal distribution. And you can see that on this QQ plot, the quantiles, so the blue markers, the quantiles which were obtained from the sample, they match with the normal quantiles quite accurately, as they should, because this sample was actually drawn from the normal distribution. So that's how a QQ plot should look like if your residuals basically are indeed normal. But now on this panel on the left, I have a QQ plot which was constructed using a different sample. And in fact, in the panel on the left, the sample was drawn from a chi-squared distribution. So here again, the blue markers, they are the quantiles which were obtained from the sample. The red markers, these are the quantiles from the normal distribution. And you can see that there is quite a fair bit of discrepancy between the quantiles from this sample and the quantiles from the normal distribution, suggesting indeed that the data did not come from the normal distribution, and as it should, because these data were drawn from a chi-squared distribution. So basically in such a way you can use the QQ plot to assess kind of the normality of your residuals and potentially pick up any problems with your regression. So in the context of time series analysis, suppose that you were working with a non-stationary data, so suppose that you had a time series which had an upward trend in them. And suppose that you were trying to estimate a model by which you would be regressing this non-stationary series on the lag of itself. So since this series is non-stationary, doing so would basically give you biased estimates. And if you were to do the QQ plot for this particular data, you would get a picture like this. So again, the blue markers, they show the quantiles of the residuals that you would obtain from this regression. The red markers are the quantiles from a normal distribution, and you can see that particularly in the lower tail and in the upper tail of the distribution, there is quite a fair degree of mismatch between the quantiles of the residuals and the normal quantiles, suggesting that your residuals do not appear to be kind of normally distributed. And again, that can be interpreted as signs of trouble. In this case, this trouble is driven by the fact that the fact that you're using kind of non-stationary data. So in that way, QQ plot can be quite a useful tool to kind of do this quick and dirty assessment of your regression model. So I should emphasize that QQ plot, that's not a formal test for kind of non-stationarity or for the goodness of fit or your model. So you don't have a level of significance or a level of confidence or a p-value attached to this test. So that's just like a very quick thing that you can informally look at to get a sense in practice of whether or not your model fits the data well. So the question is, well, what do we do if we have kind of non-stationary data? Because as I mentioned, as it happens to be kind of a very large, great many of time series data actually happen to be non-stationary. Well, it turns out that it is very helpful in terms of resolving non-stationarity, in terms of dealing with non-stationarity. It is very helpful to actually understand as to what is the nature of this non-stationarity. So as a first pass, what you may want to do is to ask yourself, well, what does the nature of the stationarity in this data look like? So is it that the mean of these data is changing? And if so, in which way it's changing? Is it trending upwards? Is it trending downwards? Is it trending upwards in a linear way? Or is the variance, or is it, for example, the variance of these data which is changing? So for example, suppose that in the most simple, in the simplest possible case, of non-stationary data, you can have data which has a linear trend. So you may get a data set where the variance of your data doesn't really change, but kind of the mean of the series tends to go up or down at a constant rate over time. So in this case, we would say that we have a linear trend in the data. Well, perhaps the most common and easy way of dealing with trends and linear trends in particular is by differencing your data. So just by working with the data, not in the level form, but in the form of the differences. So for example, for our series, if we wanted to kind of remove that trend from the time series, we could create a new time series which would be constructed as the differences between the realization of our time series, our yt, and the first lag of these series. So that would be the first difference of this series. So then instead of estimating a model where we regress the series and the lag of itself, we can estimate the model in the first difference form, but would be regressing the difference of the series on the lag of the difference. And again, if you do that, in the case of the linear trend, this should do the job. And in fact, in difference form, the series is going to be stationary. And the way to check whether or not, in fact, differencing did the trick and you're getting stationary time series again could be the QQ plot. So for example, in practice, if you were faced with a problem like this, you could estimate the model in levels, look at the QQ plot, see that the residuals are not normal, suggesting that you have a problem with your data, then difference the series, estimate the model using the differences, and look at the QQ plot again to see whether differencing actually successfully resolved the issues which you had with your data. And in some cases, what you may find is that differencing once is actually not enough, so you may still have indication that you have problems somewhere even after working with first differences. So sometimes it may be necessary to work with higher order differences, for example with second difference, where second difference is just the difference between the difference of the time series and the lagged difference. So it's the difference of differences. And you could estimate your time series model in a second difference form by regressing the second difference of your series on the lagged second difference. You'll be regressing difference in differences on the lagged difference of differences. And again, potentially you could have even more fun with it, so you can look at higher order, like third order differences, or you could also look at percent differences. And the appropriate choice, the appropriate level, kind of degree to which you would want to difference the series, that would be determined by, again, you could use the QQ plot as the diagnostic tool to determine the appropriate degree to which you should difference your series. Now, differencing the series is a good way. It's a very simple way of dealing with non-stationarity, but it has one limitation in that it kind of removes the trend from your data. So your different series, if they're stationary, they by definition are not going to have any trend. But for some applications, you might actually be explicitly interested in the trend. So you might actually think that, well, not ignoring, but netting out the trend from your model is actually bad because you're purposefully interested in the trend. Maybe you'd like to forecast the trend, maybe you'd like to estimate the trend. So sometimes you may be kind of more explicit about the trend, and in that case differencing might not be the best option. So another thing which you can do to deal with the linear trend is you can explicitly include a regressor in your model which would kind of take that trend into account, and we would call such a regressor a trend term. So if the trend in your data is indeed linear, what you can do, you can include time. So your t, time, you can include that as a regressor in your model. So it will have its own slope coefficient, beta 3. And then you'd estimate this model by regressing the level of the series on its own lag and by regressing it also on time, again, as one of your regressors. And once you do that, you could again look at the QQ-plot and see whether or not basically including a linear trend term, in fact, was successful in resolving the non-stationarity issues. So, for example, if after you estimate this model, you do a QQ-plot, the residuals look normal. So based on that, you may kind of conclude that yes, indeed, the trend in the data was linear, and the inclusion of the linear trend term successfully captures that trend. So now I'm happy with my model estimates. So this is an example of a residual QQ plot that you would get if you included a linear trend term into our previous example. So you would no longer get these differences between the quantiles of the residuals and the normal quantiles. So if you recall, I'll quickly flip back. So if you recall, when we estimated the model without the linear trend term using these data, we had a bit of a problem, so that we had a misfit. Our residuals were not normally distributed. But once you throw in the linear trend term, these differences, they do go away. So now the residuals actually do appear to be normally distributed. So we're kind of content with that. Now, this is, again, including a linear trend term is very simple. And it works, except that it only works if your trend indeed is linear. So in many data, the trend might not, in fact, be linear. So the trend might be, for example, an exponential trend. So things like population or GDP might be growing at an exponential rate. And in this case, including a linear trend term will still not produce you the QQ plot as that you should be getting. So including the linear trend term might not be sufficient. So in that case, basically, what do we do? So that's an example of an exponential trend, again, when the mean kind of of your series is increasing, but it's doing so at an increasing rate. So in this case, again, what we can do, we can explicitly take this exponential trend into the account by including a separate trend term into the model, so another trend term into the model. But now, instead of just including time as a regressor in this model, we're going to include an exponential of time as one of the regressors into this model. So it's going to get another coefficient, which will be the exponential on time, and we'll be attempting to estimate basically the model. Now, using this nonlinear, using this exponential trend term as one of the regressors in this model. And then again, as a diagnostic to see whether or not this exponential trend term is correctly capturing the trend in our data, we can look at the resulting QQ plot for the residuals from this model. And again, if they look normal, we could say that, well, indeed, it looks like that exponential trend term is correctly capturing the trend in our model. So far so good. We have basically linear trends. These are easy to deal with. We have exponential trends. These are also quite easy to deal with. You just have to include a an exponential trend term into your model as opposed to the linear trend term into the model. But what happens when we have kind of more elaborate, more involved type of trends? So many data tend to exhibit some kind of a seasonal cycles, or they could be business cycles, for example. So if you look at some kind of weather data, you're likely to see fluctuations which are seasonal. So some cycles that your data go through at a yearly frequency. If you look at economic data, for example, such as output, you may see that basically output will fluctuate, but now not at an annual frequency, but at some kind of a longer frequency corresponding to the business cycle. So there may be examples of trends in the data which are not exponential, which are not linear, but which in fact kind of appear to be cyclical. So in this case, if we just toss in a linear trend term into the model or an exponential trend term into the model, this will not do the trick. So we will not be able to capture a trend of that form, basically, using the previous two methods. But there is still some things that we can do to successfully deal with trends like that. And in fact, there are two approaches that we can adopt. So we can do the differencing in a fashion which is very similar to what we've done before to get rid of the linear trend. And we can also attempt to include an additional trend term into the model, but which now will capture these cyclical trends. So the approaches are the same, but the specifics, the details are going to be quite different. So when you're working with the data which you suspect to have some kind of cyclical behavior, some kind of a cyclical pattern, perhaps the first thing that you may want to ask yourself is, well, you may try to determine as to what the frequency is of the underlying cycles. So in some cases that might be an easier task than in others, certainly. So if you're working with weather data, for example, if you're looking at annual temperatures, it's pretty clear that the frequencies of your cycles are most likely to be annual. So the cycles are probably going to repeat themselves every year. But in some other data, such as economic data, it might be a lot harder to judge what actually is the relevant frequency, the length of the cycle. But so either way, you'd have to make some kind of a judgment call as to what the frequency appears to be. So I'm going to use little s in terms of notation to denote the frequency of that cycle in periods of time. So for example, if our data are monthly data, if we have monthly data, if we want to look at cycles which happen with annual frequency, the corresponding frequency will be 12 months, so that's 1 year. If we have monthly data but we want to look at cycles which happen with quarterly frequency, then the corresponding frequency will be 3 months, so 1 quarter. So once we make some kind of a decision about the frequency of these cycles, what we can do is we can convert our series from the level form into the seasonal difference form. So instead of taking the differences between the values of the series and just the first lag of the series, we're going to look at the differences between the values of the series and the lagged value of the series, which is lagged by the frequency periods of time. So for example, if we want to calculate annual differences of the series, we're going to look at the differences between the values of the series today, let's say in April 2013, and the values of the series 12 months ago, so 12 basically time periods ago, so in April 2012. So before we would look at the differences between April and March. Now we're going to look at the year-over-year differences, so April 13 versus April 12. And these differences we're going to call seasonal differences. So the key idea here is that if indeed the trend in your data is cyclical, and if indeed you chose your cycle frequency correctly, once you calculate these seasonal differences, the resulting series, so the time series of the corresponding seasonal differences should be stationary and should not have any kind of cycles, any trends present in it. And again, the QQ plot can be used to check whether or not that's true. So you can estimate the model using the seasonal differences and then look at the QQ plot of your residuals to see whether you still have any problems with your data. So in practice, it might involve a bit of experimentation. So you might, for example, try different cycle frequencies and then different reasonable cycle frequencies, and then kind of try to choose the one that seems to give you the QQ plot, which looks kind of the most normal. And again, I want to emphasize that the choice of cycle frequency may not always be an easy one, so it may require a bit of experimentation. This is probably where doing econometrics can be a little bit like an art as opposed to the science. There is really not going to be like a clear-cut rule book that you should always follow that will always give you the right answer. But again, so seasonal differences will help you kind of net out any seasonal trends. And for some applications, that might be sufficient. But then in other applications, that certainly might not be sufficient because you might actually be explicitly interested in seasonal trends. So you might actually want to explicitly estimate some kind of a seasonal or cyclical trend. You might want to forecast the seasonal or cyclical trend. So in some applications, you might want to be very explicit about this cyclical trend and actually include a term into the model which would be able to capture this cyclical trend. And the way in which it is usually done is through the inclusion of a cyclical trend term into the model, which is based on the sine wave function, on the sine function of time, on the sine function of t. So this function is parameterized by 3 parameters, by beta, omega, and theta, where these 3 parameters are going to control the cycle amplitude. So the parameter beta will control basically the distance between the peak and the trough of your cycle and your data. The parameter omega, that's going to control the cycle length. So that's essentially is your frequency. And the parameter theta in this wave function, that's going to control the phase angle. Essentially, that's going to control the starting phase, the phase at which the cycle is going to start in your data. So if you're working with, for example, seasonal cycles, that parameter would control kind of the season at which your sample would, the trend in your sample would start, whether your sample starts in summer or in winter or in the fall. So I'm not going to go through the details, but you can show that this sine function, this sine function of time, it actually can be expressed as a sum of two terms, as a sum of a sine which involves time and a sine and a cosine which involves time. Now the thing to note here is that this function is also a function of s, of the frequency of the frequency of your cycles that you chose before in periods of time. So for practical purpose, again, if you want to include a cyclical trend in your model, and if you'd like to use that the sine function to model the cyclical trend term into the model, then you can augment your model by including this trend term into the model, which is a sum, again, of two functions, a sine of time and a cosine of time, and which also depends on the cycle frequency, your little s, which you chose. So for example, suppose that we had annual data, suppose that we had monthly data, and suppose that we wish to include, we suspect that in these monthly data we do have quarterly trends, so we do have some cycles which last for 1 quarter. So in this case, the corresponding frequency would be 3 months, 1 quarter, and if we wanted to include, to model these quarterly cycles using that sine function, we would include, again, this following term into the regression model, where now the frequency, the denominator in these two fractions, would be set to 3, so 3 months. If we had monthly data and we wanted to capture annual cycles, we would do the same thing, except that now our frequency would be set to 12 months, 1 year. And again, we would include that term into the regression model, which would capture these annual trends using the sine wave. But now the frequency, that denominator here, is going to be 12. And if we had daily data, for example, and we wanted to model monthly trends in these daily data, again, we could do that in the same way by including that sine function into that regression model, except that now our frequency would be 30 days, 1 month, so that basically denominator would change. That's really the only thing that would be changing if you were to adjust the cycle length. So now we saw basically that it's possible to deal with linear trends, it's possible to deal with exponential trends, it's possible to deal with cyclical trends. But that puts an interesting question as to what happens when you have, when you combine these trends. So what happens when you have a data series which has, let's say, a linear trend component, it may have an exponential trend component, but in addition to that, it also has a cyclical trend component. So here I have a simulated time series which has both a linear trend component, so you can see that kind of the long-term average of the series is trending up, but it also has a cyclical trend component, so you can see that it tends to kind of wiggle around in repeated patterns, wiggle around this changing average. So basically the question is then, what do we do in this case? So again, to solve a problem like that, we can resolve to differencing. One approach could be to difference several times. For example, to first attempt to net out any seasonal trends by calculating the seasonal differences of your series. And then attempting to net out the linear trends by calculating the first difference of the seasonal differences. So then the final regression model, which you would be estimating, would be to regress the first difference of the seasonal differences on its own lag, as opposed to regressing again the levels on the lag of the levels. So basically combining the seasonal differences with the first or the second differences could be one approach to resolving an issue like that. And again, the QQ plot can be a useful diagnostic tool to check whether or not you've been successful in netting out the effects of these two trends by doing this type of differencing. But in some cases, again, we want to be explicit about the presence of the trends in the data, and we actually want to augment our model such that it is capable of capturing both of these trends, both kind of the linear trend component and the seasonal trend component. So what we can do, in fact, is we can include all of these trend terms that I've covered over the past few slides. So the linear trend term, the exponential trend term, as well as the cyclical trend term. We can include all of these trends into the model and estimate the model where we would be regressing the level of the series on its lag then on a linear and an exponential trend term to capture any kind of a linear trend or exponential trend in these data. And then additionally regressing that on a cyclical trend term to capture any kind of a cyclical component present in these data. And then UT, of course, is your residual term. So then you can estimate this model, obtain the estimates, look at the residuals, and again, if you see that your QQ plot appears to show that the residuals from that regression are normal, you can interpret that as kind of evidence to suggest that you have correctly captured all of the trends, both the linear trend and the cyclical trend in this model. So, and that opens up an interesting door, because if you obtain the estimates of all the coefficients in the model, so say you were to estimate this model and get the estimates of all your betas, so beta 1 hat through beta 7 hat, it opens this, an interesting possibility. It actually enables you to forecast trends. So not just to forecast the series, but you can forecast the values of the trend components. So for example, suppose that we want to predict the value of a linear trend component at some period in time, capital T. Well, we can use the estimates from the previous regression model to do that. That's just going to be the value of our trend term, evaluated using our estimate of the relevant coefficient of beta 3 hat, and times the value of our time variable, which we're interested in. And in exactly the same way, we can predict, we can estimate the value of an exponential trend, again by just plugging in the values for time and plugging in the values of the relevant coefficients from our model into that expression for the exponential trend term. And the same thing, the things would work pretty much in the same way if we were to predict a cyclical trend. So given the estimates from this model, we can predict the value of the cyclical trend at certain point in time, capital T, again by plugging in the coefficient estimates into that expression for the cyclical trend term, which is, in our example, was based on a sine wave, on a sine function. So when you look at some of the data which have been kind of detrended or demeaned, what has been done to these data was that the people who constructed this data series would first estimate the model which explicitly included all of these trend terms. Right, so for example, if we want to remove the effects of a cyclical trend and the effects of an exponential trend from the data, we can first estimate the model which includes an exponential trend term and which includes a cyclical trend term. We can then calculate the estimates for the exponential trend term and calculate the estimate for a cyclical trend term. And then we can calculate the detrended values of our series by subtracting the values of the corresponding trends from the values of the series. So for example, if we want to have the series with the exponential trend removed, we can construct the new series YT bar by subtracting our estimates of the exponential trend. And similarly, if we want to have the version of the data series which have the cyclical trend component removed, we can do that by subtracting our estimate of the cyclical trend component from the value of this series. So that would be an example. In this case, we could say that if indeed our cycles are based on seasons, that could be an example of a seasonally adjusted data. And given the forecasts for the values of the trend, given the estimates from the previous model, nothing of course stops us to actually generate a forecast of the series themselves. So if we want to predict a value, if we want to generate a forecast for the time series at a certain period of time based on the value of the series at time t, so suppose that we know yt, we can generate a one-step ahead forecast for this time series just by plugging in the coefficient estimates into our regression function and by plugging in the estimates for our trend terms, so the linear trend, the exponential trend term, and the cyclical trend term. And that basically will give us the forecast of the one step ahead forecast for this time series. And here I'd like to touch on another topic that quite often comes up when you're doing applied work with time series. So oftentimes you may be presented with several models which have reasonably similar degree of complexity. And suppose that the objective of these models is to generate some kind of a forecast. And here the issue would be is basically, well, how do you judge which model is actually doing a better job at forecasting than than the different model. And there are several approaches which you can take. To this, so I want to cover a few. So one measure of kind of forecast accuracy, which is very widely used, and you may have used it, I'm sure, in your work in the past, is the so-called root mean squared error. So the difference between the value of the series at certain point in time and the forecast and the predicted value of the series, which is kind of generated by the model, this is your forecast error. So ideally, of course, we would like to have zero forecast errors. Ideally, we would like to be able, our model, to kind of predict the data with 100-degree accuracy. Needless to say, that pretty much never happens. So any model will be producing some kind of a forecast error. So then, in order to judge kind of the overall propensity of the model to make errors, you can look at the average squared error and take the square root of that, and that'll precisely be the root mean squared error. So just the sum of all of the forecast errors squared divided by the total number of observations in your sample. Take the square root of that. That'll be a measure called root mean squared error, which will capture kind of the average propensity of your model to make errors. And then again, as I mentioned, ideally we would like the model to not make any errors. So in the best possible case, all of the errors are zero. Therefore, in the best possible case, your root mean squared error would also be zero, but that's not feasible. So in practice, what you would like to choose is you'd like to choose a model which gives you the smallest root mean squared error. That's not the only approach, though, which is adopted so that to evaluate the accuracy of the forecasts. So in some cases, you want to be a little bit more elaborate as to how you judge the errors. So, for example, in some cases, if your model makes a positive error, so for example, in some cases, if your model kind of underpredicts the data, that's not really a big problem. But in some cases, if your model makes a negative error, so if your model actually overpredicts the data, that is a bit of a problem. So, for example, if you're forecasting some kind of a macroeconomic data, or if you're forecasting risk, for example, suppose that you were doing a project for the bank and you were using a time series model to generate some kind of a risk forecast. Well, in this case, your preferences over this error are going to be highly asymmetric. So if you kind of over-forecast risk, that might not be that big of a problem as if you under-forecast risk. So if you're kind of better prepared to face the risk, that's not all that bad. If you're not as well prepared to handle the risk, that might drive your bank to bankruptcy. So in that case, you might be very kind of averse to only certain types of errors, either positive or negative errors. And to capture that asymmetry over the to impose the asymmetric penalties over the positive and negative errors, a construct known as the Linux loss function is used. So this Linux loss function, again, that's just a function which assigns a certain penalty to the model error. It's parameterized by one parameter a, and the way in which it works is that when the value of your parameter a is greater than 0, positive errors are penalized very heavily, but negative errors are not penalized as heavily. And similarly, when the value of this Linux parameter is less than 0, basically you'll be penalizing negative errors severely, but you're not going to be penalizing positive errors as much. So based on the application, sometimes when evaluating basically, yeah, and then if you'd like to get an idea of kind of the overall predictive power on of the model, but now taking these asymmetric preferences of the model error into the account, you can look at the sum of these losses that your model is making, the sum of these Linux losses, and that would be a measure, again, of the propensity of your model to make losses. Now adjusted again for these asymmetric penalties for positive and negative errors. And then, of course, you would want to choose the model that gives you kind of the smallest cumulative error. So you may want to choose the model which gives you the smallest cumulative Linux loss. So I just want to do a very quick recap. So today, basically, we talked about the issue of stationarity, non-stationarity. And really, the key takeaway from that is that you have to be very careful to not use non-stationary data, or to make sure that you're taking non-stationarity into the account in an appropriate way, because if you don't, you may get unbiased estimates. You really may get spurious regression results. Now, a useful diagnostic plot, which can be used as kind of a quick and dirty way to see whether or not you have any problems with your data or with your model specification, is a QQ plot. So again, I want to emphasize that it's not a formal test for non-stationarity or kind of model specification. It doesn't have a level of significance attached to that, but it's just something that you can get very quickly. So I think in most modern econometric packages, you can generate a residual QQ plot with literally 2 clicks of the mouse. So it's something that's very quick to do, and oftentimes can be quite helpful as a diagnostic tool. And again, if you do find that your data have trends, there are multiple ways in which you can deal with that. So differencing is one way, and again, these could be either kind of the first difference, the second difference, seasonal difference, or in some cases you might want to look at percent difference. But also, in some cases, you may want to be explicit about the modeling of the underlying trend, and you actually may want to include the trend term directly into your time series models. And kind of if you're presented with several versions of the model and you'd like to kind of judge as to which of these models might be preferred, the 2 statistics that you might be looking at is you might be looking at the root mean squared error for each of these 2 models. And then in the case in which your preferences over error are asymmetric, again, suppose you don't really care about the model over-predicting, but you really care about the model under-predicting, you may capture these asymmetric preferences by using a Linux loss function, basically to gauge the performance of the model in this case. So if you have any questions, I'm more than happy to answer them.
The time series that I follow is the unemployment rate. So these are seasonally adjusted. Adjusted by the month, I assume. Could you tell us the logic of adjusting unemployment rates for seasonality?
Right.
And whether there would be alternative ways of doing it that economists would discuss as to which would be better, and especially if you're looking at times over different historical periods. Would different kinds of seasonal adjustment make sense at different times?
Right, right. So I should say that I don't know exactly how Stats can be doing their seasonal adjustments. So on my end, I can only give like general comments and in principle how something like that could be done. Basically, in employment, you may have a lot of kind of regions with many seasonal jobs. So if you look at like eastern regions like fisheries, there's a lot of some jobs by nature are seasonal because you can only do them at a certain kind of at a certain season. Or if you look, for US, for example, some recreational jobs down south, they might have a very strong seasonal component because everybody takes vacation at a certain time. Because some jobs are traditionally done at a certain season because of some natural constraints, or maybe the demand is such that the demand for these jobs really peaks at certain season, and then you have a low season. So that's the reason why you may have kind of seasonal fluctuations in employment numbers. So that's what the Statistics Canada is trying to adjust for. So it tries to remove that kind of seasonal component. So broadly speaking, I would imagine that they're doing something similar to what I've shown over here. So they're trying to estimate that seasonal trend and some kind of net it out, remove it from the series. So they try to get an idea of exactly which variation in the series is due to that kind of seasonal variations in employment, and which is due to other factors, and they're trying to separate the variation which is due to the seasonal fluctuation from the variation due to other factors. So basically that's what they do when they seasonally adjust it. In terms of how that changes, how that procedure changes over time, I don't know how Stats Canada changed their seasonal adjustment processes, but I would imagine that over time they might use different approaches to so I wouldn't be surprised, for example, if 20 years ago they used a different approach to backing out the seasonal component in their unemployment series than they do today.
If linear trend and the exponential trend are controlled in the regression at the same time, is there any problem of multi-collinear or other issues?
Yeah. So, basically the linear trend term and the exponential trend term will be correlated by construction. They will be highly correlated, so you will get a problem with that. But again, that's a feature rather than a bug. So, there will be correlated, so you will have an issue with multicollinearity. Essential and unavoidable because they're correlated by construction. Yeah.
They are all correlated to time.
Yes. Oh yeah.
So the OLS will be balanced.
No, in this case, you'll still get unbiased estimates, but your variance estimates are going to be not as they could be if you didn't have a multicollinearity.
Could you comment on if you have in time series data, we have missing data?
Right.
Is there a way to get around to see how we can handle that?
Yeah. So there are multiple ways in which people tend to fill up the gaps in data. So you can try and impute the values of the data in one way, and there could be many approaches, each with kind of different consequences. You can either take the average of the nearest certain number of nearest neighbors to get the value for this data, or you can try and estimate the model, for example, dropping the observations where you have missing data, and then based on these model estimates, you can try and come up with an estimate for the missing value in your data. So there could be a number of approaches that you could take here, both parametric and non-parametric, to back out some missing data. But one thing I should also caution, and that's not only applicable to the issue of missing data, but also with working with kind of seasonally adjusted data, is that suppose that you were to, let's say, to come up with some estimate of the missing data point, but suppose that in the process of developing that estimate, you've used other data points. So now that estimate, that's basically a function of all the other data points in the sample. So it's no longer an independent observation. It's no longer an observation which is independent from other observations in the sample. In the context of trends, you have to be careful because when you estimate the trend, that estimate of the trend, it depends on all of the observations in the sample. So the detrended observations are no longer independent from each other because they all share this kind of trend component which was stripped from them, but this trend component was a function of all of the other observations in the sample. So that's something worth keeping in mind, that when you're working with seasonally adjusted data, when you're imputing the data.
I'd like to go back to my unemployment rates.
Oh yeah.
You indicated some elements that would be clearly part of it, which is that certain industries would be seasonal, and of course there's other things, and you indicated that these may vary by region. And so since this kind of trying to report unemployment rates by region and even by census metropolitan areas, I assume, and then also there would be questions of supply, that is supply of labor, when students are no longer...
Oh yes, yeah, oh yeah, that's great.
Looking for work, and so they might boost the unemployment rate. So how would it be best to do, and we get the seasonally adjusted rate every month.
Right.
So how much value should we give to that seasonally adjusted rate? Would they adjust it for each city separately, or would they do it just a kind of a basic adjustment over the country, or they produce unemployment rates by regions, not by industry. So they wouldn't have that by fishing and et cetera. But they could do it separately for each province, or would you recommend that they would do it separately for each province and census metropolitan area?
Right. So I don't know exactly how Stats can do it, but to me it certainly seems that it would be a good approach, a very thorough approach, if you somehow attempted to estimate the seasonal or cyclical trend components separately in each province, and then aggregate them into one kind of seasonally adjusted national unemployment rate. And also on an aggregate, so economy goes through business cycles, and also, so even though kind of the regions fluctuate independently, the national economy may fluctuate at a bigger frequency. So there is a whole bunch of kind of cycles which are going on in these data. So I think in principle, it would certainly be good to take all of these into account. Whether Statistics Canada does that, I do not know, and the feasibility of that I also don't know. That would largely depend on the data.
If there's no other questions, thank you very much for a very thorough and very well organized presentation. Easy to follow.
Thank you.
Very much.